All right, so repeating this, I guess, the video's starting. We're going to talk today about the two topics that I maybe naively thought we could cover last time. But today we're going to talk about generators and three-phase power. There are a lot of elements of power systems that are probably relevant to sustainable energy and smart grid systems. These are sort of two of the many options. You can also talk about things like transmission lines. But we're just going to focus on these two. I think these kind of cover a lot of what you need to know practically about power. And given this course is not on electric power systems, but just has a small unit on electric power systems, hopefully this gives a fairly broad coverage of the topic and kind of explains some of the big issues at hand. Remember, generators are how we make power, and three-phase power is how power is transmitted in the grid. So if you look at big transmission lines, you notice they all have three kind of separate groups of wires, and those are all each carrying a separate phase of power. So it's good to know at least what's going on there. And then, as I said, we'll talk about problem set 1, but this will be off video. So if you're not in class, then just try to watch it elsewhere. I guess you don't get to see the discussion about problem set 1. So let's get started with generators. Were there any questions from last time? OK, great. Were there any questions from last time about AC power, actually, before I jump into this? Hopefully I covered questions during the time there, but if you have questions, please do come to the office hours next Monday or other times. And you can take a look at the homework too and see how sort of practicing with it a little bit might help a lot with that. All right, so generators. Generators are how we actually produce power in the grid, right? You might think of power as coming from, oftentimes when we sort of do small circuits, you think of power as coming from AC sources or DC sources. And these are DC or AC voltage sources. And to a first approximation, something like a generator or a battery, for example, could be thought of as a voltage source. But really, this is not a very good model of what's actually going on. And when we talk about generators, you actually want to talk much more about controlling power and controlling, I guess, power and voltage really for AC systems. But hopefully we'll sort of describe the basics about how large generators work to the point where we ultimately do in a building have AC source that is a reasonable approximation to a voltage source. I mean, it's about 120 volts, again, RMS voltage there. But what's really happening kind of behind the scenes on a larger scale are these big generators that are making this power. So good to know about how these work precisely. So the simple example is one that you probably have seen before, and it's kind of the simplest example of a possible generator here. You can actually make these out of magnets and paper clips. So if you've ever done that in like a high school class or a grade school class even, they're kind of fun to see sort of just spinning a little magnet and making some electricity. But the basic idea is that if you have a magnet that rotates within a loop of wire, this will create a current in the wire, or a voltage in the wire if there's nothing connected here, but if there's some load, it'll create a current then. And the reason is, we're not going to get too much into physics here, but if you have taken a physics course on electricity and magnetism, you'll remember that a moving magnetic field will create an electric field at right angles to that magnetic field. So the rule everyone does here, that all the engineers do, right, is you use the right-hand rule. So if the magnet in this case is rotating this way, and this is one positive side, and this is a negative side, but we won't worry about which is which, because I'll have to end up flipping it otherwise. But if the magnet's rotating this way, you can think of the current or voltage being generated, or the current that will flow through here, assuming this is connected to some load, as flowing this way through the loop of wire, right? And this creates, when the magnetic field is moving like this, it will create this current that flows in that direction because it creates this this electric field at right angles to this magnetic field. And so what you get is if you take a magnet and spin it in a loop of wire like this, what you get is this alternating, really sinusoidal voltage signal that looks just like this. And so AC generators are actually quite simple because sort of a spinning magnet naturally wants to generate an alternating voltage signal. That's one of the reasons why they're kind of nice to generate power of this type, is that we don't have to worry about things like, if you've seen things about DC motors or DC generators, you have to have things like brushes or sort of things here that can kind of change to make sure that you're always generating current in one direction. But an AC generator is actually quite a simple thing, because you just have this rotating magnet within this loop of wire. And this is, again, a cartoon picture of what these things actually are, but it's a reasonable picture of it, too. So remember, what happens here is this, right now, this magnetic field is rotating this way. It's rotating clockwise. So when this sort of bit of wire here, what it's experiencing is this magnetic field is kind of rotating this way, and so we'll want to create a current that flows this way through the wire. And the other thing happens, and so that's sort of at this point here, when it's maximally aligned, it will be creating the maximum current or maximum voltage in this case. If we're just assuming there's maybe no load connected there, it would still create a voltage. And as this thing rotates, the actual sign of this voltage will vary, and so the strength of this voltage will vary, and it will do it exactly sinusoidally. So when this is standing straight up, there's no actual apparent magnetic field that's seen by these two wires, and so there's actually no voltage being created. And similarly, when you're on the other side here, this wire is sort of like this picture upside down, though, right? So this wire is seeing a magnetic field going this way, so we'll want to create a current going that way to the thing. So current will go this way when the magnet's over here, and it will go this way when the magnet's over here. And so what that looks like in terms of the voltage signal is this very nice sinusoidal voltage property measured at these two endpoints here. And this is sort of one of the reasons why, well, there's a lot of reasons why AC power is nice. The big one is actually about transformers. Back in the day, we had easy ways of stepping up and down AC voltage very easily, and stepping up and down AC voltage and current. But this is also kind of a nice property here, right? We can easily talk about making a generator like this that will create a very nice AC voltage. Now, in reality, generators are a little bit more complicated than this in a few ways. The first one is that you will never actually just have a single loop of wire here. That would be very, very inefficient. What you actually have is many, many loops of wire here. And what that does is that essentially each wire sees the magnetic field again, and so you end up adding those voltages you effectively have, and so you end up increasing the voltage that is actually being output here by having these many wires. So that's the first big difference in these called windings in the case of a generator like this. So that's the first big difference. You have these multiple windings to this loop of wire here. But just to give a little bit more notation, and actually I should have mentioned this slide first. So a little bit of notation here. The rotor is the rotating element. So that's, in this case, the magnets making things, providing the moving magnetic field. The stator is the stationary element on the outside. So stator is stationary and rotor is rotating. Nice terminology there. This next one is not as obvious. the name doesn't give it away as much. But the armature is the actual wires that are carrying the current. So this is the armature here. Now, the armature, which are the wires that carry the current, that can be actually either in the rotor or the stator. Right? You could actually have magnets on the outside here and rotate some wires in the middle. That would work fine, too. But you typically don't do that. And the reason is that the voltages on the outside here are actually pretty big, and you typically don't want to have that high voltage wires here just kind of spinning around and moving a lot. It's typically, you want to keep those stationary. So almost always, I believe, some people might actually know this better than me if there are any generators that actually have a rotating armature, but I don't know of any. The armature is the part that carries the current, but that's usually in the stator. And a key term here, which I'm kind of simplifying a little bit, is what's called a synchronous generator. So in class, we're just going to talk about synchronous generators. And the real key part here is that, technically what this means is that the magnetic field, the magnetic field and electrical field are moving in sync with the actual rotating movement. But what it means in practice is that, in some sense, this generator has to be moving in sync with the grid as a whole. That's sort of an easier way of thinking about it. It has to kind of be synchronized to to the grid. So the grid is at 60 hertz, right? The grid is, in the U.S. at least, in other countries it's different. But in the U.S., the grid is, we assume that power, or we require that power has to be delivered at a frequency of 60 hertz. Sorry, voltage and current have to be delivered at that frequency. And so what this means is that these generators, synchronous generators, have to spin at, well, you would think they have to spin at that same speed. That's not quite true. If they had to spin at 60 hertz, that means they'd be going about 3,600 RPM, which is pretty fast for a generator to move, certainly. What they do instead, actually, is use multiple windings in the actual system, so that essentially you have, I don't think I actually have a picture of this on this one, but if you look at sort of the generator from a head-on perspective, and so you have your magnet here, what they actually will have is they will have multiple pairs of windings. And what that means is that each of these pairs of windings effectively sees, if each of these pairs, if you add multiple sort of poles to this actually, let me say this a little different way. Let's actually, instead of doing this, let's actually have multiple poles of our magnet. So let's actually talk about having a magnet that has multiple poles here. So there's a magnet, you actually have more than one magnet effectively. And if you do that, then essentially these guys here will see more than one magnet going by per rotation. So they'll see more than one full revolution per rotation of this system. So you can actually have this thing rotating at a slower speed while still having these guys effectively output, for example, 60 hertz power. And that's done by having multiple poles in this magnet here. It does still, the key point though is it is still moving in sync with the grid. So it's not moving at a different competitive rotational speed. It's probably moving at some fractional amount of this. So maybe say 1/8 of 300 RPM or so. That would be a more reasonable speed for a generator to be actually moving at. But again, synchronous generators have to move in sync. There are other types of generators too. For example, in a wind turbine, you couldn't do this, right? Because the wind turbine kind of rotates. I mean, it has a fixed speed that it wants to rotate, but that actually is dictated by aerodynamic effects, not by the speed of the grid, right? It would be crazy to try to make all wind turbines spin at exactly the right speed for the grid. And so there are much more complex forms of generators that exist for systems like this, but we're not going to worry about those. We're really going to focus on synchronous generators, because most big sort of typical generators where you have some direct control over the actual rotor itself, those typically are set up in a synchronous fashion. It just makes things a little bit easier, and there's less losses involved there. Now there are a couple changes you make to that sort of basic idea of the generator to get kind of a reasonable approximation of what a lot of generators actually look like. The first is this multiple poles in the magnet, so they don't have to spin at 3,600 RPM. They can spin much slower. And the other thing is that instead of a permanent magnet as on the rotor, we typically want to use an electromagnet. And the reason for this is that there's a few reasons. A, it's just they're oftentimes easier to make. Permanent magnets for large-scale things tend to have to be made out of kind of rare earth materials. Not always, but sometimes. Or they require some sort of more exotic materials, typically, to make them of the strength you would need in kind of a grid-scale generator. And the other big one is that with an electromagnet, we can actually increase and decrease the strength of this magnetic field by increasing and decreasing the current that flows through this loop of wire here. So an electromagnet is just some substance that can be magnetized with a coil of wire going around it. And just like the moving magnetic field created an electric field, a moving electric field around this will create a magnetic field through this magnet and magnetize this whole material here. Now, well, actually, before I say that, there are a few caveats to this. When you use a system like this, you have to have some way of actually creating this magnet to begin with, right? And in particular, you need, to create a magnet, you need a DC source of energy, right? If you actually had AC flowing through here, it'd be changing the magnetic field back and forth at whatever frequency. That thing would be spinning through this. That would be kind of a mess. It would look really, really gross, what you would actually get out in terms of the voltage coming out of that. So you really want a DC source of electricity here to actually create this electromagnet in the rotor. Now, that has to come from somewhere, right? So we need some source of DC power. And that can either come from a separate generator that we have. Maybe we have just some separate generator that we're running as a DC generator to power this thing. Or we could actually just draw it from the grid and then convert to DC power. We'll talk later in the class about how you convert between AC and DC voltage and current. But the disadvantage of that, if you just draw AC power from the grid, is that in some sense this can't start up on its own, right? You would need kind of to have an electric grid already going before these things could start. So if every generator in the country was drawing from the grid to create its electromagnet, that would probably be a bad thing, because if every generator went out, we would have no way of starting these up again. And so generators that, or rather magnets that use a separate generator to create that, usually with a permanent magnet, that one maybe, because you can't go on forever in terms of having these more and more generators with more and more magnets here. But if you use say a DC generator with a permanent magnet to create this electromagnet in the bigger generator, that generator will have what's called a black start capacity then, because it can start up from a black hour. It doesn't need any external source of power in order to actually start moving. The second nice thing about the electromagnets is that, as I said before, we can change the strength of this magnet by varying the current that flows through this loop of wire here. And that's actually very important, because what that does is when that magnet gets stronger, what we essentially see, what we get from that is actually more voltage, higher voltage in the wires of the generator itself. And so a very nice property of electromagnets that we would not get with a permanent magnet is that we can actually vary the output voltage of these generators when we use an electromagnet. As I said before, the last thing we sort of do in practice is that you don't want to have just one loop of wire going around here. You actually want to have many loops, and that will amplify the voltage by a fixed ratio, the number of loops that you have. And from all these things, we can get these generators operating at pretty high voltages. Things like 10 kilovolts, stuff like that are very, very common in big generators. Then we step it up even higher to go to the actual transmission system, but generators themselves can be quite high voltage already in the stator itself. Okay, so any questions about this? This is sort of, this is a very high-level presentation of it, because we're not going to get into, for example, the physics of magnetism and precisely the equations that govern these things. Those are very important, actually, especially when you talk about losses of generators, because when you talk about a loss, the losses have to come from somewhere, right? And there's a lot of, when you're doing this conversion between electricity and magnetism and converting back and forth, there is some loss, actually, in these systems. The things that gives off things like heat, and these things can get very, very hot in practice. And so all these issues are very, very important, but we're not really going to delve into too much detail about the actual physics behind generators. Just trying to give you a basic idea of how they operate. What is important, though, is understanding how generators, in some sense, create or generate both real and reactive power. Remember, real and reactive power are really key components to AC systems, right? We have this real component, this reactive component. But there's not a real great sense in which you can really generate reactive power. I mean, it sounds even kind of funny to talk about generating reactive power, right? Because by definition, it was power that was consumed and produced every time. But it's important to understand how these devices actually do, in effect, control both the real power and the reactive power elements of a system. So to start off with real power, remember, there are two things we can directly control in a generator. Actually, I didn't said this yet, but there are two things we can control. The first is we actually do have some sense of being able to directly control the real power of a generator. And this follows just from the conservation of energy, right, or conservation of power in this case. Mechanical power and the real power, real electrical power, have to be equal. Real power is what's actually being consumed here. It's what's actually being used to do some work somewhere else. And so in order to conserve energy, the real power that we're putting into the generator by pushing on that magnet has to be equal to the real power that's being consumed by that actual generator, or by the loads that the generator is powering. And so one way of writing that, for example, is that we can just make an equivalence between the P, which stands for real power, remember. P will stand for real power always, and Q will stand for reactive power. So P is just the real portion of this product of voltage and current. And it has to equal the torque we apply to the system times the rotational velocity of the generator. That's just the equation for power of a rotating system. Right, remember, for a linear system, this would be actually, it would be force times velocity. But for a rotating system, it is torque times rotational velocity. So those are the two things we can control, really, to control real power. We can either control the rotational velocity of the system, or we can control the torque on the system. And those things have to multiply to equal the real power that our generator is producing. Now, we know, though, that in a synchronous generator, we can't change the rotational velocity. Right? That is fixed. And we're assuming we cannot deviate. We really, really don't want to deviate at all from that. And that would be really bad. So the only thing we can really control then is the torque we put on the system. So essentially, you just push harder on your little crank there, and so in order to keep it at the same speed, and that will provide the amount of real power that is necessary. Now again, in some sense, if you want to keep it at the same speed, there is just a sense where you have to apply a certain amount of torque, right? But the amount of torque you have to apply depends on how much real power is being consumed by all the loads attached to the system. So if you attach a much bigger load to it, or a load with higher real power consumption, you will have to push a lot harder to maintain that same rotational velocity. And so what happens in practice here is that there's very, very tight control loops. And we'll talk about control a lot more later on in the class. But essentially what happens is the way we apply, say, more torque to a system is that, in the simplest example of like a water turbine or a gas turbine you can think of, right? There are sort of valves we could just open and shut that would just allow more steam or allow more gas into the system. Those will effectively push harder on the rotating rotor, and that will increase the torque. And so what they do in practice is they look really, really closely. Remember, the goal is just to maintain this rotational velocity and apply whatever torque is necessary to supply the real power that sort of is being asked for by the different loads attached to it. So what you do is you look at that rotational velocity very, very frequently and very, very closely. If instantaneously someone hooks up a new load to a system, what will happen is that there will be a because we haven't increased torque yet, what will happen is that the rotational velocity has to start decreasing a little bit. So this has to start slowing down. So you hook up a new load and this will start slowing down a little bit. We will see that in our system, and to counteract that, and we have to do this very, very quickly, you have to open up more of those valves, which will essentially increase the torque, which will then maintain the rotational velocity. Does that make sense to everyone, sort of what's happening here? Because in some sense, the power that it has to generate is dictated by the loads on the system, right? So if you attach a new light bulb to this generator, that will need more power. Now, at first, you will be kind of applying the same amount of power to this crank. Pick up that new light bulb, and so therefore what will happen is that the power has to equal this still, so you'll actually start slowing down. It won't slow down immediately because there's some just momentum to the system, which is actually what kind of saves you in the very, very short term. But pretty quickly, this thing will start slowing down, and kind of the frequency of this rotational velocity will start decreasing. And so in order to counteract that, and to maintain the same rotational velocity, you have to have some control system that will open up, say, more valves in our turbine, and push harder on that crank, and therefore keep it going at the same speed. And that's the way we maintain real power in a system like this, in a generator. Does that make sense? Is there any questions about this a little bit? I think, yeah.
Why does adding a load make more power?
Why does it make more? So it makes you need more power.
Oh, okay.
Right. So if you add a load, then you need to generate more power. So basically, the power is required. The power that's being generated has to be the same as the power being consumed. The power in the generator has to be the same as the power that's being consumed by the different loads that are attached to it. So if you add a new load, you essentially are increasing the power that's being consumed by the loads. And so therefore, you have to increase the power that's being generated by the system itself. The way you do that is you increase the torque on the generator itself, and that will bump up the power generation to sort of maintain its equilibrium here. Yeah?
So if you don't care about the frequency, you can just keep it running and you'll still be able to?
Yeah, well, so it's sort of strange, right? So technically, what would actually happen is that you just don't have enough power. I mean, you have to generate the power, right? So you could actually, so in order to generate more power, you could actually have to increase the frequency, right? That's what you would need to do to maintain with that same pushing, same torque. To provide more power, you actually have to increase the frequency. Now, so what I'm talking about in terms of this thing slowing down is the fact that the natural reaction, sort of just by physics, to try to essentially, you aren't producing enough power to satisfy demand, so that will start taking energy out of the system, and that will, well, I should be careful about energy and power there. But basically, that will start, the effect of adding a load instantaneously will be to start slowing down the system, but you don't want to just leave that, because then that will just sort of essentially slow it down to a point where it's just not going to be providing as much power to all the loads, and the loads just won't get as much power. What you would see in practice then is actually voltage drops, and you see a change in if you just let things go the way they would, what you would see actually is you would see a change in the voltage the generator is actually producing, which would change the power effectively too, and that would bring things to balance by essentially providing less power to the loads. So loads are resistors, right? But they aren't power, they don't suck up a fixed amount of power, right? They just say, for a voltage, I'm going to consume this much current, and that gives you power. What would happen then is essentially the voltage would go down, so these things would actually start consuming less power. They would have to bring power in balance. If that doesn't make sense, don't really worry about that too much. The basic idea here is that we have to keep the power that we're producing in balance with the power that the things want to consume. And especially if we want to do that while maintaining voltage, we need to increase the torque on our system. Yeah?
In a small scale, the rotational velocity fluctuates around 60 Hz.
Yes, very, very slightly though. And this is exactly why it fluctuates, right? Because people turn on loads. You turn on a load, and you don't phone up the generators before you turn on a load and say, I'm about to turn on my light bulb, get ready for it. You just turn things on. What that causes instantaneously is a slight slowing of the actual frequency. And so there is a deviation. And when lots of people do this, I mean, there is a sort of a random element of power at a large scale. And what that causes in the generators are these very slight deviations from the desired frequency. The way they account for that is exactly by having these tight control loops that just immediately start accounting for it, adding more force and more torque to counteract that change in frequency. If you take loads off, by the way, this will start speeding up. The opposite things happen, right? If you just shut off a light bulb, they'll start speeding up at default, so you have to start applying less torque to keep things in equilibrium.
Is there any allowed margin?
Yes, there is. I just forget exactly what it is. Does anyone know what the allowed margin for frequency regulation is? It's pretty small, right? It's, what was that? 0.5 hertz? Okay, I didn't realize it was that big. They really allow it to go that much? Okay. It doesn't ever get that high, though. I don't think I've ever seen 60.5 hertz. Yeah, so maybe this is sort of like that's the requirement, but it never gets that bad in practice. What was that? Okay. Yeah, so I guess I don't know that for sure, but people here can be experts in certain things, certainly, so I'll trust that until someone tells me otherwise. And repeat it as I will from now on. Yeah, so I mean, that's still a relatively small amount, right? From 60, if the margin is in fact 0.5, it's a relatively small amount. And it happens because there can be sort of big load increases. It's also made a lot more complex when you have many generators operating simultaneously. So in a little bit, we'll talk about actually situations where you have multiple generators, where you actually have to think about the flow of power through networks. And we'll talk about power flow and those things, which make it much more complicated, right? Because if each generator tries to act on its own, you might have problems. You might have situations where they can go unstable and things like that. But certainly, yes, the single generator case is simpler, but you still have the same kind of effect of things slowing down and speeding up. When you have many generators, it's actually interesting because if one starts slowing down, the rest will kind of help it. It sort of is generating less. It needs less power. Everyone else will start generating more power or providing more power, and so it will then start speeding up. So you have this natural equilibrium that's actually maintained by many different generators, but you can also have things like situations where this whole system goes unstable and starts oscillating the frequency, and that's very, very bad. We don't want to encounter situations like that. But it just becomes more interesting, really, all the scenarios you can have. I guess the last thing is, if it's not clear yet, sort of what really creates, what causes the force on this rotor, right? I'm talking about, so you need to push harder. That's not really obvious. Well, why do you have to push harder, right? It's just rotating at a constant speed. And what happens is that just like the rotating magnetic field creates that current, similarly, when the current flows, it will create a magnetic field that opposes the actual rotation of the system. So when current starts flowing, so if there's nothing attached here, you actually will need no power, right? You can spin because there's nothing resisting it. It'll create a voltage difference in these two terminals here, but there will be no actual current flowing, so nothing actual, no work really being done in any sense. When you have current flowing, though, that creates a moving magnetic or electric field then, and that creates, again, using this right-hand rule, a magnetic field that will oppose the direction of rotation of the rotor. And so, in order to keep the rotor spinning at that same speed, there actually is a force opposing it, and so you have to apply force to keep it spinning at that speed, at a fixed speed, fixed rotational velocity. And that, I think, is all I'm going to say about real power. So remember, real power is sort of the actual physical power we're putting into the system. We need to put it in because it's caused by these magnetic fields here. And we have to put it in at an amount that balances out the resulting loads in the system, or we start having problems, like it starts speeding up or slowing down. The little bit trickier element to think about is what's the situation with reactive power. Remember, reactive power is not something that generators can actually really think about producing, right? Reactive power is kind of this weird thing. It happens when you have inductance or capacitance in the system, and so you need to, in some sense, provide the ability of loads to handle this, but it's sort of unclear what we mean by that. I mean, why does it matter in some sense if the voltage and current get off out of phase at a load? Why does that really matter? It's not quite clear. The other thing is, how do you go about producing that is also not really clear, right? How do you account for the fact that you have some inductive load in your big chain that's going to get things out of phase? What we do control directly is this power we apply to the rotor, and we also control the voltage of the system. Remember, we can control the current that flows through this magnet here. That changes the strength of this magnetic field, and that changes the voltage coming out of our generator. And what we're actually going to do is we're actually going to use voltage to effectively control real reactive power in some sense. But that's a little bit of a confusing statement. Hopefully it'll be a little more clear when we talk about power flow also. But I just want to give a simple example about what's happening here that hopefully will make this a little bit clear. And this example summarizes the situation, so hopefully it's helpful to see. So suppose we have, in this case, a voltage source. That's not quite what we're talking about before because we don't quite have voltage sources, but we can control the voltage again by controlling the current that flows through that electromagnet in the rotor. So we can think about setting this voltage in some sense. Let's just think about an AC voltage source. It goes through two things. It goes through an inductor and a resistor. So it goes through an inductor, and then it goes through a resistor. The inductance of this thing is L henries, and the resistance of this is just going to be R. So we can apply Ohm's law to the system. Remember, Ohm's law said that the voltage, and this is the voltage source. The other thing I'm going to look at is also actually the voltage directly across this resistor here, which is going to be VR. Now, these will both be complex numbers in general. Remember, voltages for AC systems and currents are complex numbers. But let's just think about sort of what this looks like in some sense. Okay, so we can apply Ohm's law to this system in sort of two ways, right? We know that Ohm's law has to hold for the whole thing. So Vs has to equal the current flowing through this whole thing times the impedance of the whole system. Now remember, the generalization of Ohm's law for AC power systems was that you had resistance plus the imaginary unit times J times omega times L minus, I guess, 1 over C, 1 over omega C. That was, remember, our generalization of impedance was R plus J omega L minus 1 over omega comes the capacitance. Here we don't have any capacitance. Let's just talk about inductance. So you just have this expression here. So V of the source equals the current flowing through it times R plus J omega L. We can also write the same thing for just this part of the system here, right? The current flowing through all these things is going to be the same. So we also have the equation that VR equals I. And here we don't have any inductance. We just have the resistance. So we just have this. So now we just solve for I here and plop it in here. And what we see is this equation here. We see that the voltage over this resistor equals R over R plus J omega L times the voltage of the source. The important part is that this ratio can actually decrease the magnitude of this voltage. So by adding the inductor here, we have effectively, this resistor sees less voltage than it would otherwise. So if we want to provide the same amount of real power to this system, if we want to say, okay, we want to have the absolute magnitude of the voltage, rather the real portion of power here, which is the voltage times this current, if we want to keep that the same, we have to actually increase the voltage being provided to the system. What this sort of means intuitively, and again, I recommend going through this example and start checking all the quantities here if this is all confusing to you, because it certainly took me a little time to sort of wrap my head around the first time I saw this, certainly. But essentially what's happening is that this inductor is actually causing us to see less effective voltage at this resistor here. And what that means is we have to do one of two things. We could just increase the sort of the power, which would increase the current maybe. But what you really should do is actually increase the voltage in a way that kind of overcomes that inductor here. So you want to increase the voltage so that you sort of, this R here sees the same effective voltage as it did before. It'll be a little out of phase, but it'll be the same effective voltage. And you do that by increasing the voltage source. And so it's really talking about more about voltage control, but it really, you can think of it as generating real power. Sorry, generating reactive power for the system. So when increasing the voltage, you are effectively providing, in some sense, reactive power to this system. You're accounting for the fact that this inductor takes out some amount of power. If you had a capacitor, it would be the opposite, actually. This would be increased, because this would be a negative sign here. So in that case, you would actually need to decrease the voltage to provide, or to sort of, I guess, this is sort of also part of the convention about why we talk about capacitors generating reactive power and inductors consuming reactive power. That's because adding an inductor here means you need to increase the voltage to effectively generate more reactive power, whereas adding a capacitor would be the opposite effect. So this is one of the trickier parts to understand about reactive power. I think from a high level, the idea is you have two knobs in your system. You have the amount of torque you can apply, torque times velocity, really, transportation velocity, but really it's just torque that you have control over. And you have the ability to control voltage. And somehow you have to use both these things to control not ultimately voltage and power at the end, but you really want to control real and reactive components at the end. So loads that have inductance in them and kind of consume reactive power, you have to account for that by changing your voltage and your power you apply to the rotor. But again, this is sort of one of the trickier examples. It'll hopefully become more clear as we go through power flow, because then you'll actually start solving these equations, and you'll see that in order to, you can't control the reactive power generated, again, sort of in quotes, by a generator. What you can control is the voltage and the real power. But by controlling those two things, we actually still are able to account for consumption of reactive power on the loads. Yeah?
So basically, if we just attached the resistor, we would have needed more real power, so more torque.
Yes.
And then also attaching an inductor, we need more reactive power, so also increases the voltage.
Yes. Right. To see the same effective voltage here, if you want to sort of maintain effective voltage, so it sees the actual same voltage at the end, you have to increase the voltage that's being generated due to these inductors in line. And we want that, right? We want to be able to see 120 volts. We don't want that to change and sort of, you know, same power but different voltages here. That wouldn't be good. So we want to actually have these things appear to have the same voltage everywhere. So the only way we can do that really is by increasing the voltage at the source. Again, these voltage will not be, these two will not be in phase anymore. But in terms of magnitude, to keep those the same, the magnitude even, you have to make sure that you do that. Yeah?
So you said if you had a capacitance instead of an
Right. So capacitance is kind of weird because you add the inverse of it, right? So normally you actually would put capacitors in parallel with, or sorry, yes, in parallel with them. That's sort of the more standard way of doing it, because capacitors are 1 over this term, right? So you typically actually add them in parallel, or sorry, in parallel, not in series. That's the more standard thing you'll see. But yes, that's exactly sort of what's happening. Capacitors in parallel, and you have to do this, a great thing to check. Probably should have been a homework assignment, but it's not a homework assignment, unfortunately. Would be to put a capacitor in parallel there and see how that changed things as well. Capacitors in series will do something as well, but it's just a little less common to see that because it's a little less intuitive what they're actually doing.
And in that case, you have to decrease the voltage.
Yeah.
Because capacitance.
Yeah. So exactly. So capacitors essentially boost voltage, and inductors will decrease the voltage. Again, these are complex numbers, so they decrease or increase the absolute amount. The radius there in polar form, it increases the absolute value of the magnitude, and the capacitors in parallel will increase it. So exactly, so that's the sense in which capacitors in some sense provide reactive power and inductors consume real power. Yeah.
So torque control has nothing to do with reactive power.
I mean, yes, to a first approximation, right? They're actually both going on here because in order to, you can think of them kind of as separate systems, but I'm sort of thinking about this in terms of if we want to provide the same amount of power at the same voltage here. You could also provide the same amount of power here by letting the voltage drop, but increasing the sort of the real power component, making it spin faster. That would give you a higher current. But yes, to a first, and usually the way that power systems are usually thought of is that yes, the voltage is what is used to control the reactive power, and then the torque applied to the system is what's used to control the real power. Okay, so let's make sure we get the three-phase power before end of class today. Maybe I'll talk a little bit about the homework, well, if there's time. Okay, so three-phase power. In practice, you don't just have one set of windings on a generator. Almost all generators in the US actually have 3 sets of windings. They have one like this. So I'm again showing kind of a single pole magnet, and in addition you'd actually have multiple pole magnets. But just talking about the windings now, you actually have 3 separate sets of windings in a generator. And what this looks like in terms of the different voltages and currents that flow through it is you have 3 different sine waves now that are all 120 degrees out of phase with each other. Okay? So why on earth do we do this? There are a lot of good reasons for it, and I think it actually makes a lot of sense that we do it this way, but it isn't immediately obvious why we want to have 3 phases of power. Why not 1 or why not 2 or 4 or whatever. So let's just talk about what you would need to do to actually get power to some sources over here. So the simplest case, let's say we're going with these 3 phases of power for whatever reason. We decide we want to use 3-phase power. So you have your 3 phases. They each come out from separate wires of your generator. And each of them go to a load. I'm using this sort of, I'll use this rectangle here to talk about a load that could have both inductive and resistive elements. Or really, actually, this could be any impedance here, then, really. So some impedance we go to. And you'd have to have a return wire, right, to actually complete that circuit and have the current actually flow through this. And so you need 6 wires to send your 3 phases of power over these lines. Now, transmission lines are really expensive, so it's not clear why you'd want to do this, right? You're sort of having a lot of power moving out and coming back 3 different times. Why on earth would you want to do that? So let's do a little trick now. And we do this trick by noticing the following very nice property. If we have 3 current sources that are all the same, so you have 3 amounts of current that are all the same, and so they're the same in their absolute value, and they're all 120 degrees out of phase with each other, It's pretty easy to show both from just trigonometry, but you also just can verify it in a few seconds in MATLAB. That if you add these things up, to take all three phases here and add them up, that will always equal 0. Okay, so 3 sine waves, 120 degrees out of phase with each other. You add up their instantaneous values. So look at this point right here. You see this one, these two. That's 1, and that's -1, and that's 0.5 twice. You add them up at 0. That's true for every point along this axis. And it follows this from pretty simple trigonometry laws. In fact, it's true really for, turns out, any number of phases greater than 2. And we can show that geometrically in a second, but it's actually not that hard to show. I mean, in the case of just, think about just 2 phases that are 180 degrees out of phase with each other, right? They're just opposites then. So clearly those always add to 0 for 2 phases of power, 180 degrees out of phase now. And it ends up being true for any number of phases of power. And we'll actually very shortly see a very easy way of proving that graphically. Now, as I said, you can derive this from trigonometric identities, but it's also pretty easy to show using our complex representation of power. Remember, we talked about, voltage or current, not power yet, but talking about voltage and current as being complex quantities. In this case, I guess I was talking about current multiplying to equal 0, but the same is true for voltage. Yeah, of course. Sorry, adding to equal 0. So suppose we have 3 different voltages, 120 degrees out of phase with each other. Now we can represent those as sine waves, right? We don't talk about that before. But it's also possible to represent them as a single complex number, each of them. And you can, in fact, draw them in the complex plane. So the voltage, same is true for the current, but I'll not go and talk about voltage. The voltage of the first phase is, we'll just call that one the one that has 0 phase angle, right? So that has 0 phase angle, it has some magnitude and 0 phase angle. The second phase has a phase angle of 120 degrees. And the third one has a phase angle of 240 degrees. So the total of this whole thing, I guess, is 240. And this is what they look like in a complex plot, just showing their real and imaginary components. And the nice thing here is it's very easy to visualize what happens when you add these 3 things together, right? They clearly sum to 0. And so this sort of complex representation actually gives us a much easier way of proving this. You can just take these 3 complex numbers, add them up, and see that they do in fact always equal 0. You don't have to worry about signs anymore. Or I mean, I guess this is trigonometry really, but you don't have to worry too much about it. You can just visually see those clearly add to 0. So any sum of voltages here will always add to 0. So this is actually very nice, because what it means is that we can actually attach, after the loads, we can attach these wires all together. When we do that, assuming assuming these loads are all equal, which is an important point, but I'm going to assume these loads are all equal. Therefore, they'll all be carrying equal currents. If we just bring all the wires together, that wire will have 0 current. It has to flow through it. So this, in the simplest case, what we would do, and you'll actually, this you'll experiment directly with in the homework with 3-phase power. What you can do is actually eliminate the need for those return wires, for 3 different return wires. Or you can just make 1 return wire now, after you brought these things all together. Because the difference between this voltage potential and that one, this one's always 0 here, and this one is whatever it is from the generator. So you've effectively gotten rid of the need to have separate return wires. In fact, as you can probably guess, it gets even a little simpler because this voltage is in fact 0 here. And that comes out of the fact, sorry, this current flowing through here is actually 0. This again comes out of the fact the same thing holds for currents. So I can just replace the voltages with currents here. If all those loads are the same, all the voltages are the same, you will in fact get currents that are all the same. And so when you add them together, you get 0. That means there's 0 current flowing through this return wire. Let's just replace it with a ground. And absorb whatever little bit of current there is, we'll just absorb it into the ground. We won't worry about that. So this is very cool now, right? Because now we only need 3 wires to transmit power instead of 6. And it worked because these 3 things summed up to equal 0. And the question you should be asking, hopefully, is why not use 2 phases of power? That same exact thing held for 2 phases of power, and that's only 2 wires. Wires are expensive. We don't like building lots of wires. So why would you want to build 3 instead of 2? I'll show you, but before I get to that, I will get to that in a second. But before I get to that, I want to just describe, this is one way where you can hook up multiple phases of power and provide effectively the same current through each of the different loads. Again, assuming the loads are all the same. But it's not the only way you can do it. And this brings us to 2 common ways of hooking up multiple phases together. And they go by the name of delta and Y connectors. So don't worry about this too much, but you'll probably will see these terms again. And there's one problem in the homework that deals with this a little bit. So it's good to know what these terms are. When you hook up wires like this, and so you're hooking up the return ends of all these different loads to the same point. This is called a Y connection. And the reason why is that if you, the reason why is that if you sort of draw this in a different way, you can kind of make it look like a Y, right? Where you have these 3 things all going to a common point there. It's sort of like a triangle here, and so they call it a Y connector. And this is a common ground. And in fact, the ground's actually optional, right? You don't have to ground it. It should always be 0, but you probably should ground it in case it's not quite 0. You might want to have some, where for this current to go rather than try to circulate back into the system somehow, if the loads are not all exactly equal. The other possibility that you can do, which takes a little bit more thinking about to realize that this is in fact a reasonable way of doing things, is what's called a delta connector. So rather than hooking things up to a single ground, you could actually hook up a load between 2 different phases. So you have phase 1 here, and phase A and phase B. You could actually put a load that goes between these 2 things. And then also a load that goes between phases A and C. In this case, your loads always went between phase A and some ground. Here, your loads actually go between phase A and phase B. So this is actually a different way of hooking things up. And they get different voltages when you do this. Now, it's not at all obvious that this actually works. It's not obvious that this actually provides any kind of sinusoidal or anything kind of current or voltage here. But in fact, it does. And a nice way of seeing this is through what's commonly called a power triangle, which again uses those complex representations of power. The basic idea here is that if you start with this little drawing here of the 3 phases in the complex plane, if you hook up a load between phase A and phase B, it will see the voltage of VA minus VB, depending on your convention. It could be VB minus VA too. But what that looks like graphically is just in the complex plane, we can know how to subtract. So this line here would be, which way is it? VA minus VB. Sorry, other way around. VB minus VA. So that vector is, in fact, what you get, the voltage you see at a load if you hook up 2 phases together and let that voltage go through the load. This is you can just evaluate it, and what it is actually it's a, what would be like a square root of 3 term there or something like that, and it ends up being about 200. If each of these phases is 120 volts, then this would be effectively actually about 208 volts. And if you've seen different kind of specifications for voltages that devices can take, oftentimes they can get this by different ways of hooking up these things up in terms of delta or Y connections. So again, this is not a hugely important point here, but you may hear these words about delta and Y connections, and it's good to have like, some idea of what they are. They're useful because they essentially allow us to get power through loads without having any return lines. So remember, for this delta connection, we didn't have any return lines either. Here we didn't even have a ground, because there's no actual point here that has 0 voltage, so you wouldn't want to put a ground in. But we've still managed to get power through loads without, get current and voltage differences through loads without having more than just 3 wires going to them. So that's if you see the big transmission lines, they'll have about 3 wires going down. They may have more. Those are actually for redundancy, not for return and one going out and one returning. They're just actually carrying more in a slightly more redundant way. But that's why you see just 3 wires and not 6. Because they don't actually need to carry any return voltage. They can just carry those big 3 wires and have all the stuff for actual power sending through loads happen at the far end. Which is great because we have to build half as many transmission lines that way. It would be a total pain if we had to build a return line for every bit of electricity we want to send to a source. Sorry, to a load. Okay, so the last question is why wouldn't you want, so we talked about how bad wires are, right? I told you this thing about how these things cancel, but the other thing I said was, well, the same property would hold for 2 phases of power, right? So if you had just 2 phases here, 180 degrees out of phase, well, that would still be true. And so wouldn't 2 big transmission wires be even better than 3? Why don't we use just 2? Clearly, we want to use as few as possible. So what's wrong with 2? And the interesting thing here is about power. So remember, if you have voltage and current going through a system, the power, the instantaneous power, is the immediate product of voltage and current. So if you have one phase of power like this, one phase of voltage and a bit of current in phase with that, you will get power that very sinusoidally at double that frequency. Right, this is what we covered last time in AC power. Imagine now if you had 2 phases of power, one like this and one the opposite. Voltage also still in sync with this. Sorry, voltage and current, this being voltage, current being in phase with it. You would get 2 bits of power here that were exactly the same. So your total power would actually be varying through 1 revolution of your generator. And that's kind of nasty, right? That basically means that your generator is effectively supplying different, it's feeling different amounts of power depending on where it is in that cycle. What's very nice about 3-phase power is that what you get actually, the power ends up being 3 sine waves that are all 120 degrees out of phase. This is what it's actually pretty easy to see for just the 3-phase power, though in the homework for the 830 you'll prove whether or not it's true for more phases. But if you actually take the instantaneous products of voltage and current for 3-phase power, what you get is you actually get 3 sine waves 120 degrees out of phase with each other. Therefore, when you add the powers up here, what we know is these add to a constant amount. They don't add to 0 anymore because these are all greater than 1. But they add to a fixed amount. What that means is that your generators experience a uniform amount of torque on them throughout that whole revolution, which saves a whole lot on kind of wear and tear of the generators themselves. So really, we picked 3-phase power not because we didn't want to go with 2, or that we wouldn't want to go with 4 or something like that, but 3-phase power is the least number of phases where A, the voltages and currents would sum to 0. So you can have a Y connector or something like that. And B, the power is equal throughout that entire revolution of a generator. And those two things together are why we go with 3-phase power. You'll decide in the homework whether that actually is also true. Is power equal for, say, 4-phase power or 5-phase power? Even if it was, and it might be, you'll find out, we probably wouldn't go with that 4-phase power because that's just more transmission lines then. 3 is the fewest we could do while having this nice property of summing voltages and currents summing to 0 and having the nice property of power being equal through a revolution. So hopefully that motivates. Does anyone have any questions about that? Because I think this is actually the last slide of the day today. And then I'll start talking about power electronics next time. Are there any questions about 3-phase power? Yeah?
So you said if it was just 2-phase, the power wouldn't sum to
Right, it would not. Because so suppose you have this sine wave being voltage, and the current is in phase with it. The power actually looks exactly the same in these two cases. Power would still be a sine wave like this and a sine wave like that. So it would just be 2 of those same sine waves. They would be those 2 sine waves would be in phase with each other. The power sine waves would be in phase would be exactly in phase with each other. So they would add to times where it was really sort of a peak amount of power, and then when there was 0 power, instantaneously again. And what that corresponds to is actually needing a different amount of power through 1 revolution. So 3-phase power avoids that problem. Okay, we have a little bit of time left. I'm going to stop the tape now because we're going to talk about homework, and I don't like having the answers too much on video. So if you are watching remotely, sorry.